Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, ways to split array into good subarrays. The problem is very interesting. In this particular video, we'll be looking at two different approaches to solve the problem. One which is based on pure mathematics and second which is based on recursion and dynamic programming. I would strongly encourage you to watch the recursion part because there you will be able to understand how to firstly convert a top down solution into a bottom up solution and then how to optimize it further. So we have discussed that in multiple times in the past, but this problem will also be a good application of that technique. So with that, let's get started. The problem states that we are given a binary array nums. A subarray is good if it contains exactly one element with value 1. You have to return an integer that denotes the number of ways to split the array into good subarrays, right? And the number can be used, so I have to return it modulus 10 to the power 9 plus 7. Now we have this, let's say we have this array nums 0 1 0 0 1 and we have to split it into good subarrays. So we have these three valid splits. Now why they are valid? So let's talk about the first split. Here the first subarray contains 0 1. This subarray is a good subarray because it contains exactly one element with value 1. Similarly, second subarray is also good because it again contains exactly one element with value 1. So you can see in all other splits every subarray is a good subarray. So because that's the case, these three are the valid splits and hence the output here is 3. Any other split you will do, you will be seeing that the subarrays that get formed out of that split is not a good subarray, right? So hence the answer here is 3. So hope the problem statement is clear. Now how to solve this? So the problem involves two different things: finding out the number of subarray in each split and then finding out or counting the number of good split having I subarrays. So in this particular example, we have seen that the first split has 2 subarrays, right? Second split also has 2 subarrays. Third split also has 2 subarrays. But you might think that okay, there can be a split which have 3 subarrays or 4 subarrays, right? So we have to first figure out how many number of subarrays are there, and then for each of these value I, you will figure out how many good split exist, right? So what will be the time complexity of this strategy? So number of subarrays would be order n, right? And then for each kind of subarray, you will figure out how many good split exist with that many subarrays. So this will be at least order n, right? So this can be more than order n, but this can be at least order n. So the complexity is already very huge, which will not pass. So we have to remove this part somehow, because this we can't remove. We have to count good split anyway, so this we can't remove. Let's see if we can optimize the first piece. So the answer here is yes, because the good subarray definition is very simple. The definition is it should contain exactly one element with value 1, right? So anytime you see a value 1, that will be a part of a new subarray, right? So in this particular case, we'll have at least, or we'll have exactly 3 subarray in each split, right? So once this is clear, we now know that there is only one possible value of I for every problem, and hence this part can be completely removed. So we know that there are, like, each partition or each split will contain 3 subarrays, right? And now we have to figure out how many good split exist with 3 subarrays, right? So this is now gone and we have to figure out this thing. Now here comes the two divergence. One, we can count this via pure mathematics, and second, we can count this using recursion and dynamic programming. So let's start with the mathematics part first. So we have to count the number of good splits having 3 subarrays. So basically we have to divide this into 3 parts. So to divide this into 3 parts, we have to put 2 partitions, right, somewhere. So let's say you have this 2 bars, you have to put this bar somewhere. So you can put this bar anywhere here, and you have to put 2 bars such that the array is divided into 3 parts. So let's say you put the bars here and here. It means this is the first array, this is the second subarray, and this is the third subarray, right? So basically you have to put these 2 bars, and we have to just figure out how many number of ways are there to put these two bar, right? So where exactly you will put the first bar, or what are the possible choices or possible positions where you can put the first bar? You can either put it here just after 1. Notice that first you have to put it between two ones. You can't put it after this one, because then a single subarray would contain two ones, and that is not a good subarray. So you have to put this one, put this bar somewhere in between these two ones. So how many positions are there to put this bar? 1, 2, 3 and 4, right? So 4 positions to put the first bar. Now what about the second bar? Again, if you take the second bar, you can put it here, right, after just 1. You can put it here or here, right? So total 3 places to put the second bar. So in total there are 12 ways in which you will get there are total 12 number of good splits, and that is the answer, right? So just to reiterate, we have to divide, we first figure out how many subarrays will be there in the final split, and that we can figure out by just counting the number of ones, because the good subarray definition says that each good subarray will have exactly 1 1. So once we know that number of subarrays is 3, we know that we need to put 2 bars, because we have to partition this into 3 subarrays, so we need to put 2 bars somewhere. Now first bar we can put, or any bar we can put in between 2 ones. So number of ways to put the first bar would be number of zeros plus 1, which is now 4, and similarly number of ways to put second bar would again be number of zeros between 2 ones and 1 plus 1, so 3. So in total 12 ways are there in which we can split or partition this array into 3 subarrays, and each of these 3 subarrays would be good, because by definition itself we are only allowing 1 1 into a single split, right? So hope this entire solution makes sense. The complexity would just be order n, because what we are doing, we are just simply counting the number of ones, and then we are counting the number of zeros between 2 consecutive ones. That's what we are doing. So let's look at the code. So let's look at this code. The code is straightforward. We first figure out, okay, so notice that we need to figure out the number of zeros in between 2 ones, right? So that's what we have done. We just maintain a boolean variable whether it is the first one or not. If it is first one, we don't need to do anything. Otherwise, if it is not first one, then for every next one we need to count the number of zeros before it, right? So that's what we are doing. We just count the number of zeros, and then we check if it is the first one. If it is first one, we don't do anything, we just set the first one to false. Otherwise, we just multiplied CNT plus 1, where CNT is the count of zeros, in the result, and that is the answer, right? Simple enough, right? Now let's talk about the second approach, which is the dynamic programming or the recursion approach. So we need to count the number of good splits having some I subarrays or 3 subarrays. So what you can say is, okay, let's say the first subarray starts from here, or rather it should start from here, right? There is no other choice. Now till when the first subarray is bound to exist, till here the first subarray is bounded to exist, because it has to contain at least 1 1, right, or exactly 1 1. So till here the first subarray should exist. So first subarray can end here, or it can end here, or it can end here, or it can end here, right? So what you will do is, you will say, okay, I will put this first subarray ending here. Now tell me how many ways are there to divide the remaining array, or to split the remaining array into good subarrays. So isn't this problem exactly similar to the original problem? Original problem states that tell me number of ways to divide this entire array into good subarrays. Now we are saying that, okay, we first know, we just sliced this particular thing. Now tell me number of ways to partition this remaining array into good subarrays. Because this problem is exactly similar, we can simply use recursion here and figure this part out. So this is how the pseudocode would look like. We'll have a start position and the number of subarray we need to make, right? So for every start position, we will figure out the first position until which this subarray should extend or must extend. So we'll figure out the first one, the position of first one after this particular index. So let's say this is index I. We will figure out the first position of the first one which exists after index I. So once we figure out this index, this position, we'll know that this is one possible ending index of the current subarray, and we will try out all possible ending index. What are the possible ending index? Basically everything until we hit 1, right? So we try out every possible ending index. Now for each ending index we simply call the same function and say that okay, start from end, or basically end plus 1, start from end plus 1 and count me the number of good subarrays starting from end plus 1, and these many number of subarrays should be exist, right? Now what is the time complexity of this entire solution? Again, we can simply do memorization to skip computing the same state again and again. So time complexity would simply be the number of states or the number of unique ways in which this function can be called multiplied by what we are doing inside this function. So we are doing a for loop inside this function, so that will take order n time. Now how many states are there? Number of unique value of start is order n, count of subarray can also be order n, right? So total time complexity is n into n into n, so basically order n cube, right? Now this will surely not pass the given time constraint. We have to optimize this further. Now how to optimize this? I would encourage you to pause the video and try to think of a simpler optimization here. So we can simply remove this count subarray from here. We have discussed this technique in the last week problem as well, so just try to pause and think about this for a moment. So hope you have thought about it. What we can, as we have discussed, like we can simply remove this count subarray from this function. Why? Because this can be computed with the start index itself. So count subarray, as we have discussed, the number of good subarrays would simply be the count of ones, right? So when we say that okay, find me the number of good subarrays starting at this particular index, and these are the number of subarrays that is possible, we can simply say okay, find me the number of subarrays starting with good subarrays starting with this particular index, and inside this we can simply get the count subarray by just counting the number of ones after start, right? With this simple trick we are able to remove one particular variable from the state itself. So previously the complexity was number of states into what happens inside this function. So still we are doing order n operation inside this function, but number of states this time is reduced to order n instead of order n square. So the total time complexity is now reduced to order n square from order n cube, right? Again, just to reiterate this part, let's say you are at this particular index, or let's say this is the start index, and it says that okay, count me the number of good splits where each split will have 2 subarrays. Let's say this is what you are counting here. Now you can simply say that okay, find me the number of good split starting at this particular index. Now this 2 is something you can compute based on this s itself. How? You can simply say there are 2 ones after this, so I am sure that there will be 2 possible good subarrays. So we can simply compute this variable inside, and that's it, right? So hope this particular optimization makes sense. So we reduced from order n cube to order n square, but still this will not pass. Now what? So notice that what we are doing is we have reduced the number of states to order n. We can't do better than this. We need something here, right? At least. So we can't do better than this. Now we are iterating over all possible end index here, and that is also something which is required if we follow this approach. So this is also order n, which is something which we can't avoid. So now is the time to switch to bottom up, because these kind of optimizations will, like, to optimize this further you have to come up with bottom up solution so that you can apply some logic to optimize this further. So now how to convert top down to bottom up we have discussed multiple times in this channel. If you are following this channel, I would strongly encourage you to pause the video and try to write the bottom up solution of this corresponding top down solution. So hope you have at least tried that particular part. So as we discussed previously as well, the only difference between top down and bottom up is the way we are iterating over the array. So here we simply iterate from start index 0, and we have some base case for the end index, right? Basically we already know the answer when start is n or something like that, right? So that's where we will start our bottom up from. So we'll start bottom up solution always from the base case of the recursion, and after that we will simply iterate from backwards and apply this exact same algorithm in bottom up solution as well. So let's look at it. So we know the index of the last one, whatever is the last one is there, we know the index of that. So everything after that, number of ways to get good array would be 0, right? Because you need at least one, right? So everything after that, number of ways to get a good subarray would be 0. Now once you have all this calculated, what you can simply do, you can simply iterate from backwards, like last one index to 0, and apply this exact same algorithm again, right? And this will give you the value of result I. Now notice that because result I depends on everything after I, this result of end is something which is already calculated, and because that's the case, you don't need to like use this kind of recursion technique again. You can simply rely on what is stored in result of index, right? Now what is the time complexity? So time complexity will not change here. You can simply see that the base case, this part was order n and this part is still order n square. So time complexity is still order n square, but now we know the bottom up solution of the corresponding top down solution. Now what? We have to optimize this, right? So is this loop like what's happening in this inside this loop? Because this is a loop we need to optimize. We can't optimize this particular loop. We have to iterate over every index at least once, right? So this outside loop or the outer loop is something we can't optimize. We have to optimize this inner loop for sure. Now again, this kind of optimization we have done multiple times, so try to pause and think by yourself. So this part is exactly similar to how we do suffix sum. Only difference here is we are breaking out from the loop when we hit a index which have the value 1. So what we can simply do, we can simply say that okay, we can find out the first one after I, we can find out the second one after I, everything between it is something I have to add to my result, right? So just to give you an example, let's say you are at this particular position, so this is I, you will figure out the first position or the first one after I, you will figure out the second one after I. Now you will just sum everything here. So the result of s plus 1, result of s plus 2. These are the three things you will sum up to get the value of result of I, right? So finding out these two things are straightforward. You can simply apply one for loop and figure out what is the first one after me or what is the second one after me. This is very straightforward. I would not show the code for this, but you can simply maintain an array or a stack and this would be done. Now notice this part. So okay, this two part is I am considering order 1, assuming that we have done some kind of pre-computation and we already know what is the first one, what is the index of the first one after I and what is the index of second one after I. This two something we already can pre-compute, and this part is order 1. Now coming to this part, this is still order n, right? But now you can simply see this is just a sum in a particular range L2R, and it can be achieved very easily using suffix sum or prefix sum, right? So that's what we will do. We'll simply replace this particular part with suffix sum, and that's it. So you can see this is the exact same algorithm that we have seen before. Now instead of iterating over everything one by one, we can just maintain suffix sum, right? And instead of iteration, we can simply do suffix of end index minus start index. Now there can be like +1 or -1 differences here and there, but this is the overall algorithm. Next we'll look at the code, but I would strongly encourage you to pause the video and try to code both the bottom up as well as top down solution by yourself, because without that you will not be able to apply this kind of trick in the future problems. So I hope that you will try it at least once. So next you look at the code. The code for this particular thing is also very similar as we have discussed. We will first figure out these two things: the index of first one after I and index of second one after I, right? So next array contains the index of first one after I, next contains the index of second one after I, right? So what we are doing, we simply check whether the current index is 1 or not. If it is 1, so let's say you are at this particular position. So what is the index of first one after I? It is the current index itself, right? So we just assign next j to j. And what is the index of second one after I? You can simply say, okay, whatever is the index of first one of I plus 1 will be the index of second one at this particular position, right? So that's what we have done. Next of j would be next of j plus 1. Now let's say if it is not 1, let's say if it is 0. So in this particular case, the index of first one would simply be the index of first one of the previous element or the next element, and similarly the index of next one in the the second one in the next element will be equals to the index of next one in the current element as well. So that's what we have done. We simply assign this to the value, whatever value was there for j plus 1. Now once that is done, we need to apply this particular algorithm. So what we are doing, we will simply maintain a suffix sum and will just do a suffix sum over the indexes that we got from the first and second. So we are iterating from n-1 to 0. We figure out the first and the second, like the first one after me and second one after me. So if both of them are equal, so basically what I am doing is first, if there is no index or there is no one after a current index, I make it n. So that's what we are checking. If both of them are equal, this can only happen when both of them doesn't have a 1 at all. So if both of them are equal, there is no 1 at all after this, so we just continue. Basically there is no valid partition at all because everything is 0. If that's not the case and end is n, it means we have 1 1. So basically we are talking about the scenario where we are computing the value for this particular index. So we have 1 1, but there is only just 1 1, there is no next one, right? So for this scenario, we know there is just one valid partition. This is just one valid partition. So that's what we are doing. We just assign result j equals to 1 and just compute a suffix sum as well. After this, if that's not the case, it means we have both the ones, right? So we are at a particular index I which will have both the ones, and because it has both the one, we can simply take the sum in between them. So that's what we are doing. Because it has both the one, we take the sum of st plus 1 minus ed plus 1, basically the suffix sum of that particular range, and finally we get the result and we modify the suffix sum accordingly. So after this entire thing, result of 0 will contain how many ways or how many splits are possible starting at this particular index, and that's exactly what you want, and hence we return result of 0. So hope this entire solution makes sense. If you have any doubts in this particular problem or in any of the two solutions that we discussed, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.